Hello everyone, good morning. I'm Arvind and along with my teammates Akash Kumar and Hari Prasad, I will be presenting our project title Here the World, an AI Predictor for Relic Intelligibility. We are guided by Mrs. Alakshmi J, Assistant Professor of Department of AIDS. Now, introduction. To give you some context, over 430 million people globally suffer from disabling hear loss. For them, enjoying music often is a struggle because they distributes the relief from the background equipment. Current hearing loss are good for speech, but when it comes to music, goal to automatically predict the word correctly. WC or how many words our listener feel hearing can understand in a song of the problem. Statement of the problem. The core problem we are addressing the measuring gap. While we are having a tool to measure speech clarity, we lack effective metric to predict lyric clarity in complex musical environments. Engineers can prove hearing it for music if they if can't measure the problem. And the simple yes and no is not it. We must account for audiogram and frequencies collective losses. The production revoke the comparison your photonic details. Scope of the project relic intelligibility prediction project. Develop a reboot benchmark tools to predict the relic intelligibility score 0.0 to 1.0. Research is associative audio technology, hearing aids manufacturer, and MIR engineers. Deliverable a three-stage of AI pipeline, separable extraction fusion, a predictive regression model XGBoost validates the centers of CLPI dataset. Now, challenges. Identifying the four key challenges. Singing is substantially different from speech. The noise in music is actually structured instrument, not random stats. Hearing loss involves complex deflect like frequency loss. Modern mixing technologies often mask local intensity. Now we see methodology. Our target domain is Western pop and rock music using Agenda CLPI dataset. Our primary objective is to build a AI model to predict the word correct rate WCR. Essentially, how many words a listener with hearing loss would correct understand. This is our methodology. Now, we propose a novel three-stage of hybrid AI framework. Vocal isolation. We first separate the vocal from the music. Next, dual path analysis. We analyze the vocal using two paths, listener path, modeling the ear, and the tick cues you tick path, modeling the brain. Third step, future. We combine these insights to predict a single intelligibility score. This is our methodology. Next, we see to the architect. This is our architecture diagram. Here is our system architecture. You can see the input audio goes in Demucs for separation. The isolated vocal stem is then for feed into HSPI for and the whisper model. The output along the exotic future goes into AX boost predictor to give the final prediction. Next, we can see the design diagram. Our use case diagram shows the user uploading audio and receiving a score. The class diagram outlines the core module separator future extractor and predictor. See the implementation. This is our use case diagram. First, we have to upload a data set, then monitoring the process, and then calibrate the model and evaluate the result. And evaluate the result is the last accuracy process. This is our class diagram. A class diagram is represent of an object and in many ways. It is a simple template from which objects are created. A class from main building blocks of object-oriented application. Although thousands of students attend in the university, you should only model one class called student. We could represent the entire collection of. This is the sequence diagram. First, admin. Next, upload the audio dataset. Separate the vocal. Then extract the features. And then predict the intelligibility code. Algorithm used. We have used the three key algorithms. First one, hybrid transform Demucs for the state-of-the-art music source suppression. Open AI Whisper model, a transform-based model for reboot the speech recognition. XT Boost for the final regression task. Chosen for efficiency with tabular data. Next, implementing the detail. Hardware and software. Hardware. Language we use to 3.8 Python and deep learning PyTorch for deep nice and whisper model. Audio noise, Libros and audio acoustic feature, pitch clarity or HSAPI ML model, X boost and schedule hardware on the GPU, NVIDIA GPU for DMS and in feature, storage sufficient storage for data implementation. We are implementing this in Python. Key libraries include PyTorch for deep learning and Librosa for audio processing. We are handling the challenges like GPU memory management process for audio. Next, this is the code segment, abandoned code. This is for first. We are using the Demucs model. Then separate the vocal. This is the transcom relic transcript. This is get the relic original relic from our hearing relic. This is the out. Whisper model achieved 79.16 accuracy on the validation test. Comparison. The base model only achieved 49.13, proving the need large model singing voice. This is the output for last process. Word rate is 0.208 here. This is the represent the graph way to output our output. This is the test case and this is the result. Overall result. Compound perform whisper model accuracy 79.6. Whisper model base model accuracy 49.30. Absolute steady ASPI only or equal to 0.61 accuracy. ASR only 0.5. Final evaluation Person correlation of 0.72 on the blind test set. Last conclusion. For result we are very promising hybrid model achieve a person correlation for 0.72 with the human prediction. This is significantly outperformed the single metric baseline like AHSI and ASR only. The whisper medium model give a accuracy nearly 80% isolated work. Last reference and future works. Furthermore, investigate BS performance or even better vocal suppression quality. Genre expression. Validate the model for non-Western genre, classic, jazz, and Indian. Real world test. Validates the prediction actually early goes a clinical setting. Reference. uh, There are key reference we are used our research. Thank you for listening. We are now opening to any